Hello, everybody. I hope you're all well. And yes, our test is upon us. We'll be finishing chapter 7 today. It won't even take the whole day. And we have a test next Monday. So we'll have our problem set due already on Wednesday, and we'll have it due by Friday this week at 11 p.m. So you'll have 2.5 days to do it. All day Thursday, all day Friday, and half of Wednesday. And we'll get ready for it by finishing chapter 7. And what we have here is the precursor to synthesis. We haven't done any synthesis yet in this course. We have acetylene. We need to know how to take the proton off of this terminal alkyne. Yes, terminal alkynes end the chain with the alkyne, and they have a pKa of 25. There's the reminder down there. So we need to pick a base that gives a high yield or a good yield in the reaction below. I'm going to translate that question. The pKa of this conjugate acid of the base I choose here must be 25, or the reaction will not go the direction we want it to. Remember, pKa rules say we go from lower pKa's to higher pKa's. So I have to go from 25 towards a number larger than 25, or the reaction goes backwards. And that is the answer to this question. Why is hydroxide not a good choice? Because hydroxide becomes H2O, pKa 16. And that means this arrow, I can't rotate the arrow. That arrow doesn't go the right direction. We go away from the smaller number towards acetylene, which has a pKa of a larger number, 25. So please don't be using hydroxide to try to take the H off of acetylene. It doesn't work. So what I've done is I've come up with the pKa's all that are greater than 25. These molecules are not the answer to the question. The question is, what base will deprotonate acetylene in a high yield? And these are the acids. Their conjugate bases will go towards numbers 50, 45, 40, 35, which are all greater than 25, which means you've successfully answered the question. So I need the conjugate base of each of these species. We can go stick figures, or, I don't know, an ethyl minus there. CH double CH2. That would be a vinyl anion. I like that. Use nomenclature. Ethyl anion, vinyl anion, and this is the conjugate base of an amine, and this is going to be a little tricky. Careful. You know, English is a language where sometimes the same word means two different things. Say this as amide. I know it looks like amide, but you know an amide has a carbonyl in it, right? It's a functional group. Well, an amide is the conjugate base of an amine. It's spelled the same, but it's a different meaning of amide. All right. Or you can use hydride. H minus is the smallest one, and it's called hydride. And it goes to hydrogen with a pKa of 35. So yeah, that would accomplish the result. And these are all nice bases for deprotonating acetylene or any other terminal alkynes or other terminal alkynes. And a little motivation, why is this so important? And the answer, I'll leave you hanging. See the next page. And here's the next page. Let's let it sink in for a second. Straight from the textbook here. If I can take the H off acetylene and make acetylide, which is the conjugate base of acetylene, its role is a nucleophile in this reaction. It's attracted to the partially positive carbon here. The nucleus is what makes it positive. Nucleus of a carbon bonded to a more electronegative halogen gives this a slightly positive charge. This is attracted. And that's the most exciting part right there, making a carbon-carbon bond. That's our first time this semester. Yes, I'm very happy because I am a synthetic organic chemist, and finally we got to my realm. And we're doing hey, this leaving group, this chlorine is leaving. So it's called a leaving group. That's a good name. It's stable or else it won't leave. So we have chloride. And we made a carbon-carbon bond by doing this. Backside attacks are not solely the purview of triangles, apparently. Backside attacks happen with carbons that have leaving groups. And let's keep your life simple. Leaving groups that you're responsible for right now. Leaving groups so far, we'll just call it Cl minus, Br minus, I minus. Conjugate bases of 3 of the strong acids. That's a bit of a hint at other leaving groups in the future. Conjugate bases of strong acids are very stable. That's why they were strong acids when they had H plus on them. And here they're being generated in a different fashion, but the concept of stability is the same. And this reaction has a name. We're going to give it a real full exploration in chapter 9, where you see all these letters broken down fully like this, but further discussion will ensue. It's a substitution reaction because the carbon took the place of a chlorine. The nucleophile was responsible for that. So there's the N nucleophile subscripted there. And there are 2 molecules involved here in this step, which is the only step. It's called a bimolecular reaction. Some of you have had some kinetics and you've studied unimolecular and bimolecular reactions. We don't need to know much more than the fact that this is bimolecular. And that gives us our new carbon-carbon bond. So keeping that in mind, how could I take this molecule, which I copied here? I didn't have to draw the wedges and dashes. Those are just CH2, CH2, CH3. How could I take the H off the other side? The answer is the same as the first time. On the previous page, we had 4 ways of doing that. And then after I've got that H off, I've made an anion, which is called a nucleophile. It'll be ethyl acetylide. Acetylide with an ethyl instead of an H is ethyl acetylide. So step 1. We could use any of our bases from the previous page. I'll go with the 3rd one, I think. And step 1 gets us to here. Ethyl acetylide, which plays the role of a nucleophile. If I have a carbon that has a leaving group, then I can attack it and I will get this new carbon-carbon bond. So what's the new group I need over there? It's a methyl. I need a methyl with a leaving group. So the answer to that question is, let's have a methyl with a leaving group. Why don't we pick another leaving group for variety? Iodide attached to methyl. And there's your synthesis step. We could just do a rundown on the mechanism. Since we're here, acid-base mechanism in the first step. We've got NHCH3. Nitrogen has 2 lone pairs. I only need 1 for the acid-base step. Takes the H, you make acetylide with ethyl. It's drawn. And then the second step involves a backside attack on a carbon with a leaving group called CH3I. CH3 with an I. And we have that mechanism up there. How does it work out? We use the lone pair on the acetylide and attack the carbon with the leaving group, and the leaving group does what leaving groups do. It leaves. So here it goes. Mechanism arrow in baby blue. Hits the carbon. Iodide leaves. You've made this new bond right here. Very exciting stuff. Anytime you make carbon-carbon bonds, that's synthesis. So there we have it. We can alkylate acetylide. Does that name make sense now? Alkylation of acetylide. We put a new carbon group that's called an alkyl group. In this case, ethyl is an alkyl group. And we put it on acetylide. It's called alkylation. And how are we doing on time? We're good. We can carry on. Let's look at what we have available to us now. After you've alkylated acetylide, you can have molecules like ethyl acetylene, or you can call it 1-butyne. I'm going to sneak in review all the time. Ethyl acetylene is its common name, or 1-butyne would be the UPAC name. And if you treat it with hydroboration, with 2 sec isoamyl groups, amyl being the same as pentyl, you want to review what HB-Cia2 looks like? Here it is. H bonded to boron, bonded to a group that's both sec and iso with 5 carbons. Some stray marks, get rid of them. Oh, got rid of a lot there. It's a tricky one. Sec isopentyl is the same as sec isoamyl, AMYL. 1, 2, 3, 4, 5 carbons. Sec means a methyl on the attached carbon. Iso means a V on the end, 3 carbons. Amyl's pentyl, there's 5 carbons there. It's a bulky group on the boron for reasons beyond what you need to know, but they're discussed in the book if you want to know. And what happens is you take this terminal alkyne, which is just another way of saying the alkyne's on the end of a chain, and you will put the carbonyl on the end carbon because that's where the boron went, which got replaced with an oxygen. And oxygen in this reaction is attached to an alkene. So you have an enol, which undergoes tautomerization. See the mechanism that we spent a lot of time on last Wednesday and the day before, and you get an aldehyde. If you make the oxygen on the more substituted carbon in this reaction, the oxymercuration with water and mercury 2 sulfate, you get an enol on the more substituted carbon, which undergoes tautomerization to a ketone here. And that's good to remember because you're going to have a synthesis on your test where you have to make either an aldehyde or a ketone, starting with acetylene and smaller molecules that we're going to use for synthesis. Keep that in mind as we go to break pretty soon. If you start with an internal alkyne, we learned there was two methods of reducing it. We'll review that the bottom one, there's actually two ways. You don't have to use hydroboration and acetic acid, which we called protonolysis. You can do H2 and palladium embedded on chalk. That's palladium on top of calcium carbonate with a poison SPB2 SO4 lead 2 sulfate. 2 is Roman numeral 2 for a +2 charge. This combination over here is called Lindlar's catalyst. It does not include the hydrogen, but the hydrogens are necessary because they are here, as opposed to the reaction above, where they end up trans, and that comes from the mechanism involving radicals. Remember, that's sodium metal. That is not a sodium cation. So I don't want to see this on your test. I do not want to see this on your test. This is a unicorn, really a unicorn. Na right beside NH3 doesn't exist. Please don't pretend it does. NH3 is a neutral molecule. There's no need for a cation. If you want to have them beside each other, please at least separate them by a big space or a comma. Okay, I want to know that you know that's sodium all by itself. And remember, it has a lone electron, a single electron called a radical. So that's what you do if you want a trans alkene from an internal alkyne. And if you want a cis alkene from an internal alkyne, you have two choices: borane and acetic acid, or H2 with Lindlar's catalyst will both give the cis alkene. Keep these in mind for after break when we do a sample retrosynthetic analysis question. And I will see you after that.